The United States government recently drafted strict export controls designed to keep powerful artificial intelligence out of foreign hands. But because AI models run on borderless cloud infrastructure, enforcing those rules globally meant the government accidentally cut off its own national security agency from the intelligence tools it relies on every day. The panic started during a controlled red team exercise, where Anthropic's Fable 5 model managed to breach almost all of the NSA's classified systems. It didn't take weeks, it took hours. Having witnessed exactly what the model could do, policymakers effectively forced Anthropic to pull it off the grid for everyone, knocking out U.S. analysts in the process. The lockout highlights a growing disconnect. Policies drafted over months cannot keep pace with models that evolve in weeks. This friction at the NSA is the first visible crack in a system where legal frameworks are simply too slow to contain the technology they aim to regulate. That friction is now spilling over from government policy into the software we use to build the internet. Over on GitHub, the open-source community is facing a crisis of volume. This chart tracks weekly code submissions hitting the OpenClaw repository. In 2 months, volume exploded to over 3,400. But look at the bottom line. The actual acceptance rate flatlined at roughly 9%. Maintainers discovered that independent AI coding agents were identifying the exact same bugs and automatically submitting identical code fixes, completely unaware of each other. Open-source repositories are experiencing automated interference that mirrors the early days of internet email spam. The math of digital labor has inverted. A synthetic bot generating a code patch is now vastly cheaper than the human attention required to review it, and digital ecosystems are buckling under the sheer volume of these autonomous actions. The industry has long assumed that simply adding more data and more GPUs would lead to smarter models, but physicists looking at the energy data have concluded that our current scaling laws are hitting a thermodynamic ceiling. We are approaching the limit of how much power we can actually feed into a single system. There's also a biological limit encoded into the math. Researchers recently formalized a sublinear scaling law for plasticity loss. It turns out that as you pump more data into massive AI models, they eventually saturate. A massive neural network actually loses the ability to learn new, contradictory information after it has mastered its original training data. Realizing that raw size alone is reaching diminishing returns, OpenAI shifted its focus toward the silicon itself. In a record 9 months, they co-designed a custom chip called Jalapeño. This chip is built to run AI models, the inference stage, not just train them. Microsoft has already purchased roughly 40% of the initial production line. They are targeting gigawatt-scale deployments by late 2026. To put that in perspective, a single gigawatt data center draws as much continuous power as a mid-sized American city. With training reaching the boundaries of energy and physics, the engineering focus has shifted toward the edge. The priority is no longer just building a larger model, but manufacturing custom silicon to serve billions of users at a fraction of the cost. That brutal hunt for efficiency is forcing an equally massive squeeze in the software layer, specifically in how AI remembers long conversations. Engineers recently introduced a technique called Compress-KV. It isolates what are known as semantic retrieval heads, the specific tiny pathways inside the AI that actively hunt for important facts. Once it identifies those pathways, it strips away the rest of the memory context. By concentrating the entire memory budget on those specific heads, the model can dump 97% of its data storage and still maintain nearly perfect accuracy on complex documents. When compute becomes this inexpensive, features that used to be luxury add-ons become basic utilities. Google has now taken the ability to control a computer screen, moving your mouse, clicking buttons, and navigating apps, and baked it natively into Gemini Hash, their lowest-tier model. We even have a dedicated operating system for these bots now.
Databricks just open-sourced Omnigent, a universal meta layer designed to let AI agents from different corporate vendors collaborate inside a single network. Cleared hardware bottlenecks and compressed software have moved AI beyond the chat interface. It has become a background utility, integrated directly into the operating systems and networks that manage our infrastructure. But turning a highly capable intelligence into a frictionless commodity exposes blind spots in how we evaluate safety. A model that behaves perfectly in a sterile academic lab environment will often break the moment it touches the chaotic variables of the real world. This gauge visualizes a recent audit of top-tier AI models. In strict academic tests, the models maintained cautious, logical reasoning near 100% of the time. But when asked for practical, real-world advice, proper causal reasoning crashed to between 0 and 18%. It gets stranger when you deploy these agents in massive groups. When researchers gave LLM agents basic identities and let them interact at scale, the bots spontaneously developed strict social hierarchies and formed exclusionary coalitions without a single line of code instructing them to do so. Our current safety frameworks rely on manual audits and human labeling. These systems are not equipped to manage millions of invisible, cheap agents that can instantly organize themselves outside of human supervision. You cannot manually review billions of automated decisions a second. Surviving a gigawatt-scale, agent-driven economy requires a shift away from human oversight toward a more rigid solution. The proposed engineering solution is to attach zero-knowledge cryptographic proofs to every single action an AI agent takes. Before an autonomous bot can move money or execute code, it must generate a mathematically verifiable certificate proving it strictly followed human-defined rules. This replaces the hope that an AI will behave safely with a mathematical requirement. The burden of trust shifts from a flawed human policy to unbreakable, verifiable proofs. Artificial intelligence is no longer confined to the testing lab. It has fused with our custom silicon, our software, and the physical power grid. Our institutions were unable to slow its progress, forcing us to build strict mathematical systems to survive an intelligence that already outpaces our ability to govern it.